Welcome to Math with Malia. Today we're going to cover Eureka Squared, Math 7 and 8, Module 6, Lesson 3, Theoretical Probability. In the previous lessons, we practiced chance experiments and figuring out the empirical or experimental probability. And today we're going to talk about what theoretical probability is and how we calculate it from a chance event. Before we begin, let's review how to convert a fraction into a decimal or a percent. So for number 1, we have 30 divided by 40, and we can turn this into a percent a couple of different ways. We can just do the math and divide 30 by 40. We could also simplify and divide the numerator and the denominator by 10 first. And 3 over 4, if we know our decimals, we know 3 over 4 is 0.75. And that is 75%. We could also convert the fraction to a part to whole ratio where the whole is 100 because that's what percent means, per 100. So what do we do to 40 to get it to be 100? Well, we have to multiply it by 2.5. And if we multiply the denominator by 2.5, we have to do the same to the numerator. We would multiply the top by 2.5. And that would get us 75 over 100, which is 75%. 3 over 6, we could reduce the fraction and get 1 over 2. And hopefully we know that 1/2 of a dollar is 50 cents. And 50 cents is 50% of a dollar. Because if we take a percent written as a decimal, we can say the place value. This is 50 hundredths, which is the same as 50 over 100, which is the same as 50%. 3 over 8. Another good decimal fraction relationship is 1/8. So if you can remember what 1/8 is, 1 divided by 8 is always 0.125. So if I have 3 of those, my decimal would be 0.375. And again, we can just multiply this decimal by 100 to turn it into a percent. So we would have 37.5%. 6 over 16, again, we can simplify the fraction. So divide both by 2. 6 divided by 2 is 3. 16 divided by 2 is 8. That's the same fraction as the one before, so we know this would be 37.5%. And 6 divided by 40, we can simplify that fraction as well. 3 over 20. Now let's convert 20 to 100. Let's convert that to a percent fraction. 20 times 5 gets us to 100, so I'm going to multiply 3 times 5, and our percentage would be 15 out of 100, or 15%. Okay, number 1. Your teacher has a bag with 10 yellow, 10 green, 10 blue, and 10 red cubes. Your teacher conducts a chance experiment by mixing up the cubes in the bag and randomly pulling a cube with replacement 20 times. What that means is I will pull out one cube and then I will replace it. So we'll pull out a cube, take record of which color it is, and then put it back. So we will always have a total of 40 cubes inside the bag. And we'll do that 20 trials, 20 different times. What portion of the cubes are yellow? Well, out of the total, there are 40 total cubes. Out of the total, 10 are yellow. We could simplify that fraction and say 1/4 as a percent. That is 25% of the cubes are yellow. What portion of the cubes are green? Again, it's the same ratio, so 10 out of 40, which is 1/4, which is 25%. What portion of the cubes are blue? Same number of cubes for each color. So all of the colors would be 1/4 of the total, or 25%. Same with our red cubes, 10 out of 40, which is 1/4, which is 25% of the total cubes are red. Said to write it as a decimal, I wrote it as a percent, so we can just convert these to decimals because you will see relative frequency as decimals in later lessons. Do you think each color of cube is equally likely to be pulled? And why? Well, there are the same number of cubes of each color. So yes, it's equally likely that you will pull each of the colors. We have the same number of cubes of each color. How many cubes of each color do you think your teacher will pull? So if I pull it 20 times, and we know that each color has a 1 in 4 chance of being pulled, well, 1/4 of the total number of trials, let's convert that to a math equation, 25% of the number 20. What is 1/4 of 20? Well, it's 5. So I would expect to pull each color 5 times. Part G, complete the table by recording the first letter of the color of each cube that your teacher randomly pulls from the bag. So I'm just going to call out random letters, pretending that I'm pulling a cube out of the bag, and then I replace it. And we'll record our data in our table. Trial 1, I pull out a green cube. Trial 2, another green cube. Trial 3, blue. Trial 4, yellow. Trial 5, green. Trial 6, yellow. Trial 7, red. Trial 8, another red. Trial 9, blue. 10, green. 11, yellow. 12, green. 13, green. 14, yellow. 15, red. 16, blue. 17, blue. 18, yellow. 19, red. 20, red. So I was trying to do it randomly, just like if we were using our spinner. These are our empirical results, or our experimental data. This is what we actually pulled from the bag. Now we're going to tally how much of each color we have. So in this table, we're going to put a tally mark for each time we see each color in our frequency column. So for the red, 1, 2, 3, 4, 5. So I have 5. Reds will have 5 tally marks, and our relative frequency is the number of outcomes out of the total possible outcomes. We can simplify that fraction. It's 1/4, or a relative frequency of 0.25, 25%. Okay, let's tally our yellow cubes. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Again, 5 yellow outcomes out of a possible 20. Our relative frequency is 0.25. Okay, let's tally the green. 1, 2, 3, 4, 5, 6. Okay, 6 green out of a possible 20. We can simplify that. Divide both by 2, so that's 3 out of 10, which is 30%, or 0.30. And if we tally the blue, 1, 2, 3, 4. 4 out of 20. We can simplify that fraction, 1/5, which is 0.20, or 20%. And our percentages should add up to 100. What do the relative frequencies in the table represent? Well, the relative frequencies, again, this was after we actually did the experiment. So this is our empirical probability. Or it could be called your experimental probability. What the data actually show. Number 2, another chance experiment where we are flipping a nickel and a penny. The first step in finding the theoretical probability of events in a chance experiment is to list the sample space. So the sample space is what possible outcomes you can have. So if I'm flipping these 2 coins, we're going to just make a list of what the possible outcomes are. So we could flip the coin, the nickel could come up heads, and the penny could come up heads. We could flip the coins again. We could get the nickel come up heads and the penny would come up tails. The nickel could be tails and the penny could be heads, and then the nickel could be tails, and the penny could also be tails. So these are the possible outcomes or our sample space. Part B, what is the theoretical probability of both coins landing tails up? So theoretical probability is what we would expect to happen. What is the expected relative frequency? So we're looking for tails up. How many times do we get tails up? Well, only once, where both of them are tails. So one outcome out of a possible 4 outcomes. That is our theoretical probability, or 0.25. It's one possible outcome out of 4. What is the theoretical probability of exactly one coin landing heads up? So again, theoretical probability, what would we expect to happen? And we're looking for heads up. Just one of them needs to be heads up. Only one can be heads up, not both. So outcome number 2 gave us 1 heads up, and outcome 3 gave us 1 heads up. So 2 possible outcomes out of the 4 would give us 1 coin being heads up, which is, of course, 1 out of 2, or 50% chance of getting only 1 coin being heads up. That's the theoretical probability, what we would expect to happen. What is the theoretical probability of the nickel landing heads up? So again, we're going to go back to our sample space. Nickel landing heads up. Well, we have 2 of those options. Outcome 1 and outcome 2 has the nickel landing heads up. So that's a total of 2 outcomes out of a possible 4, which is 1 out of 2, which is a 50% chance of the nickel landing heads up. If we flipped both coins 12 times, how many times would we expect the coins to both land tails up? So first we need to think, what is the probability that they both land tails up? Well, we did that in a previous example. In part B, our chance was 1 out of 4. So we have a 1 out of 4 chance. When we do the experiment 1 time, we are doing that 12 times. So what's 1/4 times 12? We would expect that both would land tails up 3 times. If we flipped both coins 12 times, how many times would we expect exactly 1 coin to land heads up? So again, we've already figured out the relative probability, the relative frequency of only 1 coin being heads up. We did that in part C. That was a 50% chance, or 1 out of 2. So 1 out of 2 for 1 trial. If I do that trial 12 times, I would expect to see only 1 coin be heads up 6 times. 50% of the time. Number 3, consider a chance experiment of rolling a fair 6-sided die. So that means we have an equally likely chance of getting any of the numbers on this 6-sided die. How many outcomes are in the sample space for this chance experiment? How many possible results are there? I have 6 sides. I'm going to roll the die 1 time. So I can have 6 different outcomes. I can roll a 1, I can roll a 2, a 3, a 4, a 5, or a 6. Is each outcome equally likely? Yes, it's a fair die, meaning it's not weighted. So each outcome, each number is equally likely. Part C, complete the table by listing the possible outcomes for this chance experiment. So we could roll a 1, we could roll a 2, we could roll a 3, we could roll a 4, we could roll a 5, or we could roll a 6. These are our outcomes. What's the theoretical probability? What is the expected relative frequency of rolling a 1? 1 out of 6 total possible outcomes. We could roll a 2, 1 out of 6 times. We could roll a 3, 1 out of 6 times. We could roll a 4, a 5, or a 6. 1 out of 6 possible times. What is the theoretical probability of rolling an odd number? So let's look back at our model. The odd numbers are 1, 3, and 5. 3 out of the total 6 outcomes are odd. So that means we have a 3 out of 6 chance, or a 50% chance, of rolling an odd number. We could roll a 1, a 3, a 5, and that would give us the result of an odd number. What is the theoretical probability of rolling a number less than 5? So how many numbers are less than 5? Not equal to 5, but less than 5. Well, 1 through 4. So I have a 4 out of 6 chance. There are 4 outcomes that are less than 5 out of the possible 6. So we could simplify the fraction. That's 2/3. And you know that's about 0.67 if we round. What is the theoretical probability of rolling a number greater than 7? Is there a side on the die that is greater than 7? No, it only goes up to 6. So there is a 0% chance, or a 0 probability, because it's not possible. There's no side that is an 8, a 9, or a 10, or anything greater than 6. Number 4. Here's another chance experiment. The following spinner has 4 equal regions, numbered 1 through 4. To play the game, we spin the spinner 2 times, and we add the numbers together. If the sum is greater than or equal to 5, the student wins a prize. So this is similar to the experiment that we did in lesson 1. So here's a chart, and we're going to complete this table with each of the possible outcomes for the game. And you can see they gave us an example. We could roll a 2 and then roll or spin a 1, and the sum would be 3. So we're going to just finish the rest. So spin number 1 was a 1, spin number 2 was a 1, and our sum was 2. Okay, we would roll, spin a 1, spin a 2, and our sum is 3. We would spin a 1, then a 3, and our sum is 4. Okay, so we're just going to fill out this chart following that example. Spin 1 is 2, spin 2 is 3, our sum is 5. We spun a 2 and then a 4, our sum would be 6. We would spin a 3, then a 1, and our sum is 4. We'd spin a 3, then a 2, our sum is 5. We would spin a 3, then a 3, our sum is 6. We would spin a 3, then a 4, our sum is 7. We would spin a 4, then a 1, our sum is 5. We'd spin a 4, then a 2, our sum is 6. We'd spin a 4, then a 3, our sum is 7. We would spin a 4, then a 4, our sum is 8. So we've completed the table. Now let's take note. Remember, to win the game or to win points, our sum needs to be at least 5. 5 or greater. So I'm going to just highlight the outcomes that are 5 or greater. Okay, 5 or greater. Those 3 are 5 or greater, and the whole bottom row. If I roll or spin a 4, that's going to get me a sum of 5 or greater. How many outcomes are in this sample space for the chance experiment? How many possible outcomes did we have? Well, we have 4 by 4, that's 16. So 16 possible outcomes. Is each outcome equally likely? Well, yes. Remember, the spinner was divided into 4 equal sections. So each section was equally likely to be landed on. What is the theoretical probability of each outcome in the sample space? Well, a total of 16 outcomes. I could get each outcome 1 time. So the theoretical probability is 1 out of 16. What is the sum of the theoretical probabilities of all the outcomes? So if each outcome was 1 over 16, and I had 16 of those, well, I'm just going to have a sum of 16 out of 16, or 1, meaning 100%. Again, my theoretical probabilities, the total of all of the experiments of all the possible outcomes should add up to 1, or 100%. Complete the probability model by using the table from part A that we filled out. Record the theoretical probability for each sum. So now we're looking at the sums. How many times did we get a sum of 2? Just once. How many times did we get a sum of 3? Well, looking back at our chart, we got a sum of 3 twice. We got a sum of 4 3 times. We got a sum of 5 4 times. We got a sum of 6 3 times, a sum of 7 2 times, and a sum of 8 we only got once. To win the game, the sum of the 2 spins must be 5 or greater. So which of these outcomes in our probability model was 5 or greater? So these are the outcomes that had a sum of 5 or greater, and these are the tally marks. Okay, so we had it 4 times, 3 times, 2 times, 1 time. What is the theoretical probability of winning the game or getting a sum of at least 5? Well, we had 4 plus 3 plus 2 plus 1. That's a total of 10 times out of the possible 16. We could get a sum of 5 or greater. We could simplify that. That would be 5 out of 8. Number 5. A game requires spinning the following 2 spinners. You win the game if both spinners land on the same color. Dylan says there's a 50% chance of winning the game because one spinner is half red and half blue, and the other spinner is half red or blue. Explain why he is incorrect. So, what are the chances, or what's the theoretical probability of getting red or blue, and then also getting the same color for the second spin? It would be helpful if we wrote down all of the possible outcomes. So let's say first we spun a red, and then we spun a red on the second spinner. Then we would spin a red and we could get blue. We could spin red and we could get green. We could spin red and we could get yellow. Okay, then we could also first spin a blue and then get a red. We could spin blue and then get a blue. We could spin blue and then get a green. We could spin blue and then get a yellow. So these are the possible outcomes. We have 8 possible outcomes in this chance experiment. Winning the game is spinning the same color. So how many times did we spin the same color on both spinners? We got a red and we got a blue and a blue. Only 2 times out of 8. So we only win the game 2 times out of 8, or 1/4, which is 25% of the time. Another way we could look at this is if we look at the theoretical probability of each part of the experiment. So for the first spinner, we have a 1 out of 2 chance of getting red or blue. And for the second spinner, we have a 2 out of 4 chance of getting red or blue. And can you see that if I multiply those 2 fractions, I get 2 out of 8. So this is going to help us as we move into future lessons talking about compound experiments or compound results. What is the difference between an outcome and an event? Well, remember, an outcome is a specific result from a chance experiment. An event is a group of different outcomes that are related to each other. So for example, spinning the 2 spinners, each result was an outcome. We had 16 different results, but having a sum of 5 or greater was an event. It was a grouping of specific outcomes that were related to each other. What is theoretical probability? Well, remember, theoretical probability is just what you expect would happen. It's the expected relative frequency of a chance experiment. Are relative frequencies of outcomes the same as theoretical probabilities? No, not necessarily. We saw that when we were pulling cubes out of the bag. We would expect from the theoretical probabilities to pull the same number of cubes from each color. We would expect to pull 5 cubes of each color because there was a 1 in 4 chance of getting each color. But we saw in the results it wasn't quite that. We only got 4 of one color and we got 6 of another color. So relative frequencies or empirical probabilities are not the same as theoretical probabilities. Okay, that's it for lesson 3. Make sure to come back here for lesson 4 and leave any questions or comments you have at the end of this video.